So what I decided to present today is an introduction to topic modeling first and neural topic modeling after. It's work we've worked on as research, but it's not a research presentation. It's really just a gentle introduction to the topic and a very quick passing mention to Amit's work in the field. So first, a quick introduction to topic modeling, the traditional techniques like LDA and similar, variational autoencoders at large first, and then specialized for topic modeling, and then a little bit of other things around that. So as certainly all of you know, topic modeling is a famous unsupervised task of NLP that as main aim has that of finding the topics which are addressed by a collection of documents. Could be a collection of emails, could be a collection of books, could be a collection of any sort of documents. And the idea is to understand what are the main topics addressed in the collection. This is the first latent variable that is found out by the model. And the second is for each individual document to find out the topic proportions of that document. So how much of this topic, how much of this, and so forth. So that's the general idea of the aim of the task. In practical terms, what you most often do, you get your collection of documents to start with, and you compute a bag of word representation or something very similar to it. So that means you choose the vocabulary, and then for each document you count how many times each distinct word in the vocabulary occurs in the document, and you form a vector. If you say the vocabulary has V words, you have a vector with V elements that represent the document. If you have D such documents, you put them all together into a matrix, exactly like in this figure. So the first column here is the bag of word representation of the first document in the collection. The next column will be the second, third, fourth, and so forth. The sizes are typically big, like vocabularies can range in the usual range of, say, at least 2,000 words, or maybe 50,000, 100,000. These are the typical ranges for the number of rows. The number of documents can vary from a few thousand to a few million, typically. So as a matrix, the matrix itself is huge and is typically called the term document matrix, because gives you the term is the reference to the distinct words, and document, of course, to the documents. So as I say it again, the question of topic modeling is it possible to identify a small number, relatively small number of topics, say K, shared by the entire collection, and that number to be obviously much smaller than the number of the documents themselves, and simultaneously found how much of each topic is addressed by each document in the collection. So the very first cut idea can be done with simply singular value decomposition, in the sense that you can think of that big matrix, the V times D, large data matrix with all your documents in the column. You say, can I factorize that into something much smaller? Two factors, which in this case are the first and the second of those matrices. That's the first fundamental idea. Can I apply some form of dimensionality reduction, such that when I multiply the two matrices, I obtain again the same shape of the original data matrix, and I get as close as possible to its values. Of course, you can't reconstruct the values. You don't have enough degrees of freedom in the factors, but you hope to get as close as possible. As close as possible means that the error, the square error of each element, the total sum is minimized, no? To minimize, to approximate the matrix in a least square sense. So these two other matrices are really the bread and butter of topic modeling. The first one has the same number of rows as the words. So the size of the vocabulary times the size of the topics. For that reason, it's called term topic matrix. Sometimes you can even swap it and call it topic term. It's the same thing. You can transpose it. The other matrix is K times D, and K is very small. K could be 20, 30, 50. So all up, these two matrices have far fewer elements than the original data matrix. I introduced some names for these matrices because it's the names used in the papers. The presentation gets a little bit more formal in the following, so it's good to have an intuition now. W is the way to refer to the matrix, data matrix, initial data matrix. Beta is the term topic, and theta is the matrix with the topic proportions. Each column represents the topic proportion of one of the documents in the given topic set. So if you have K topics in a certain document, like that column is showing this here, these are the topic proportions of the K topics. So for that particular document. So how do you get these two matrices? If you just look at the least square solution, you apply singular value decomposition, which is an exact solution. And the problem is that the elements of the two factors can be positive and negative. SVD is not a non-negative matrix factorization technique. So if you just apply SVD, the elements of beta and theta can be negative. So the interpretation as latent variables is a little bit elusive. Still, you can use, for instance, this representation like a low-dimensional representation to compare documents. You can compare documents with K elements each instead of using the full V bag of words. You can also use for word embeddings, because if you look at the term topic matrix, each row is like an embedding, a low-dimensional embedding for that word, a K-dimensional embedding for each of the words in the vocab. So it's useful. It's a useful representation, but it's not as interpretable as what follows. Okay, so this is called, in general, has two names. It's called latent semantic analysis, LSA, and latent semantic indexing, LSI. The two techniques use exactly this decomposition. One is more emphasizing information retrieval, and the other the analysis of the collection, but the technology is identical, and it's just this decomposition. So one step up can be taken, if you just start to restrict the domain of the elements of these matrices. First, you impose that all the elements in the two factors are positive only, or non-negative. And then you also put the classic simplex constraints on each column so that the column's elements are all between 0 and 1 and add up to 1, so they can be interpreted as a proper probability distribution over a categorical variable. So in the same you do for the term document matrix. Typically you normalize the bag of words, dividing by the total sum of the words in that document so that each element is between 0 and 1, and the sum of all the elements in the bag of words is 1. So you bring them all into simplex domain. How do you find, in this case, the solution? How do you find the two matrices that are the factors? You apply a super classic expectation maximization algorithm, super easy. All the distributions are categorical. Distributions is a standard closed formula, closed form solution or equation or formula for both the expectation step and the maximization step. Just an iterative algorithm that will give you the value for beta and theta. This evolution of the model is called probabilistic latent semantic analysis, or probabilistic latent semantic indexing. So PLSA or PLSI, likewise. No? So this is when the contents become interpretable as probability distributions. We use Z to refer to the topic of a particular word, but we'll introduce this in a minute more clearly. So when it comes to the famous LDA, latent Dirichlet allocation, latent Dirichlet allocation is identical to PLSA in assumptions, but adds a prior probability over the topic proportions, over the vectors with the topic proportions of the documents, of each document. That famous prior is famously a Dirichlet prior that gives the name to the technique, latent Dirichlet allocation, and has its own parameters. It's a distribution with its own parameter, alpha. it's learnable as well. It's not that it's a prior, is fixed, is given. It's a learnable prior, because that prior is shared by the entire collection, has to be good as an average for all the documents in the collection. So all the priors in topic models can be actually learned, not because they are priors, they come with fixed parameters or arbitrary parameters. They're learnable priors. So you give this Dirichlet prior over the columns of theta. Obviously, you can also put a similar prior over the columns of beta, but the important prior is the one over the topic document matrix. Now, I think I've said all that is needed for understanding the main terms at play, but LDA is often presented in this more formal way, which is called the generative model. A generative model is a model that is completely identified. So the parameters are all given. All the parameters of your model are given. And what the model does, it generates synthetic data, virtual data, pseudo data. So essentially use the various components of your model in order so as to get data that are equivalent to those that have used it for training, to the real data, no? Synthesized from the distributions used in the model. So to be simple, the first step when you are applying LDA, the generative model, is to go to the Dirichlet distribution and sample theta. Theta is a vector of proportions with k elements, and that is used for a whole document, is fixed for a whole document. You sample one value of theta, one sample from the Dirichlet prior for each document in the virtual collection. Then you have to sample the words, but you don't sample the words directly. You first sample the topic of a certain word and then the word from that topic. So it's a two-step sampling where you first simply sample a topic from theta. One of the k values is the sample, which is equivalent to identifying one of those columns in the term topic matrix, in this matrix. By having chosen one of the values of k here, you have chosen one of these columns, for instance, this. This column represents another probability distribution over the words. It's the topic, it's this probability distribution, and you sample this distribution to get one word. So with theta fixed, you sample this column first sample the topic. So you sample one column here, and then you sample a word. Sample a column, sample a word, sample a column, sample a word, iteratively until you get all the words that you got, say n words for that document. So it's sampling theta only once, but then sampling this column, say n times, to sample one topic at a time. And from that topic, you select the column, the relevant column, and you sample one word from it. So if you sample n words in total, you first sample one topic, one word, one topic, one word, n times, okay? That's what this simple generative algorithm represents. You recognize all the distributions are there. Theta, D means the theta for that particular document. Beta is the matrix we just introduced. Z is the choice of the column. ZDN means given for that document, choosing for that word, the nth word, choosing one of the columns, and sampling in the end the word W from that column. Okay, so the notations are consistent with the notation we used in the figures.
Quick question, Massimo.
Yeah.
So is this generative algorithm, when you generate words for a document, is it for understanding better the topic of a document? Is it that?
Absolutely.
Okay.
Absolutely. It has practical uses, but in the first place is to declare the model.
Yeah.
To declare the model in a very clear way, from the ancestor nodes all the way down to the leaf nodes.
Yeah.
And this pretty much presents the model. It's obviously not a training algorithm, so it's not the way you learn the parameters from a data set.
Yeah.
Yeah, it's pretty much a declarative presentation. One thing that often actually pretty much you don't read in the LDA paper is that that step of computing the topic first is totally useless from a distributional point of view, because so if you are interested in the topic of a certain word, then you need to do that. You first need to sample Z out of K, and then sample W correspondingly out of V. But if you don't care about the topic that generates a certain word, if you just want to generate the words, the document, and you're happy to skip jump the generation of the topics, the topic variable can be trivially marginalized. Talking about two categorical distributions is not difficult. All you have to do is take the original theta for that document, the topic proportions, multiply beta, the entire matrix, compute the product between matrix beta and vector theta. You get one column that doesn't exist in the matrix, but is the linear combination of all those columns in the proportions of the topics, and then you sample n words from it. So there is no need operationally to sample the topic first and then the word, which is how you see LDA presented in every paper. You can directly sample the word from the premixed distribution, which means if I go back to the picture 1 second, imagine here you got theta, a vector of proportions, okay? You take that theta, beta, the matrix with the topic distributions, you multiply them, you get one single column, say beta mixed, which mixes the columns of beta in the proportions of theta. And if you sample the n words from it, you get a distribution which is by property identical to the one of the standard generative models. There is a reason why I'm pointing this out, is because the variational autoencoded topic models all use this product. So skip bypassing or skip jumping the Z variable, the marginalized Z, analytically, which is trivial to do by simply multiplying beta and theta to start with. So this is another view, a second view on the LDA generative model. Now, going back 1 second to the original model, the standard one, how do you train it? Just a quick description. We don't go into any kind of detail because that's not the focus of what we present today. That's not the model we target. But what you do, you use this kind of variational EM approach, which is very similar to EM in the sense you have an E step, an expectation step, and maximization step, M step, alternate until convergence, but the expectation step is not exact. Whereas in PLDA, for instance, the E step is exact. Here, the E step itself is approximated and requires variational inference or Markov chain Monte Carlo is a heavy step where you're trying to get the correct distribution, which is needed, the posterior probability of the latent variables, the Z and the theta in your model. You want to get that posterior, you can't get it right exactly, so you try to approximate it, and with the approximation, you compute the E step. So that's briefly, really, just to highlight how LDA parameters are computed. Now we come into these autoencoder topic models. So first I'll try to explain what is an autoencoder. So an autoencoder is the simplest thing you can think of. It's something that takes something in input, squeezes it into a latent representation internally, and then expands it back into the original input. So it's unsupervised because you are given some data, and all you want to do is reconstruct those data at the end. The data can't be reconstructed exactly because you limit the degrees of freedom and the nature of the distributions of the latent representation. So it's not invertible. It's exactly like PCA. If you apply PCA to reduce the dimensionality of X to Z, then Z can't give you back X, can give you back something close to X, an approximation. Or you can use noise on the inputs and try to reconstruct the noise, so the famous denoising autoencoders. There's a lot of variations around the thing, but the idea is very simple. Take X as input, compute a latent representation, and expand that latent representation back to obtain back X. That's a standard autoencoder. In a variational autoencoder, the fundamental difference is that you don't reconstruct in a physical sense anything, but you build a probability distribution P of X given Z, which means the probability of a certain observable variable given the latent representation. If the latent representation is good and the modeling of this probability is accurate, P of X given Z will be high. Your X, your input, would have a high probability in the model. If the modeling is poor, then obviously P of X will be low. P is usually in log scale, so people just measure the log probability of X given Z. This is the reconstruction performed by a variational autoencoder. It's just a measurement of log likelihood. The higher, the better. It means the fit of the model and its ability to extract Z, which can be used as conditional for the conditional probability, is effective. If instead the modeling is poor, X has nothing to do with the model, Z is poor, and P of X given Z will give a low likelihood, okay? So it's a reconstruction in probabilistic sense, not in least square sense, like the one we saw with the normal autoencoder. All right, so now here comes a tiny bit of math. This is super standard manipulation. If you don't get it, you can find it in books, explained much better than I will do. But the training of this variational encoder takes advantage of a standard approach, which is called the expectation lower bound, ELBO. This ELBO is somewhat similar, but not identical to the training objective of LDA. The goal here would be to take your X, your input, and you want the model to give it the highest unconditional probability, the highest marginal probability. So the probability of your data in the model, P of X, how well my model overall is able to model X. P of X or log P of X has to be as high as possible. So the goal of the training of these variational autoencoders is to make the log probability of the observations as high as possible. But for a number of reasons, this maximization is not doable, is not feasible. So people approach a lower bound that is instead easy to compute and maximize with the idea, no, of course, this is your target quantity, this is your lower bound means is below. As you push the lower bound up, the actual quantity has to go up by at least as much. So it has to be at least as the value of the lower bound. So it's an effective way to maximize this quantity, which you can't approach directly, by pushing up a quantity instead, you know, by property is lower than that. And you can push it up by normal maximization techniques. So what is this manipulation? I'll try to be as light as possible. You start from P of X, what you want to maximize. And you apply standard Bayes theorem involving the latent representation Z. So that means that P of X times P of Z given X is equal to P of X given Z times P of Z. You rearrange the terms and you get the first equation there, okay? Then you bring it down in log scale, because we do all this in logarithmic scale. So the log of P becomes the log of P of X given Z plus, obviously no, products become sums and division becomes subtractions. So you get that. The hard term, just to be clear, is the probability of Z given X, not X given Z that we posited before at the decoder. Sorry, I forgot to say that. I'll go back 1 second to this picture. The first block is the encoder, obviously, and the second block is the decoder that reconstructs X. So this term is the intractable term, the exact posterior of the latent variables, and we will find a quick way to get rid of it, okay? So we'll just get rid of it altogether. So this is an equality. The term of the left-hand side is equal to the sum of the 3 terms to the right-hand side. So the next step is to add another probability in Z, arbitrary, potentially, and add and subtract its logarithm. So log Q, some probability in the same variables, Z given X, but not equal to P of Z given X, which we can't get to. So another distribution in those same variables, in those same arguments, you add it and you subtract it. So obviously the equation, the quality is maintained. And then now you use the fact that the logarithm of P of Z minus the logarithm of Q of ZX can also be written as logarithm of the ratio of the arguments. For both terms, you can regroup them in the way you see, okay? So you find yourself still with 3 terms, just that now you got these denominators that you have introduced arbitrarily. And for clarity, that Q of Z given X is not a random distribution, is the distribution of your encoder, this block here. So Q of Z given X represented by that block is the Q of Z given X that you control, that you are aware of, and you add and subtract in that formula. So here you come, you got that small manipulation. The next step is to compute an expectation in Z using as probability Q of Z given X of both the left-hand side and the right-hand side of this equation. First, the left-hand side. The left-hand side is a probability of X, doesn't depend on Z. So when you compute an expectation of a quantity that doesn't depend on the expecting probability, it remains the same. So the left-hand side with the expectation remains log P of X. To the right-hand side, you got the following terms. The expectation using Q of the log P of X given Z, which represents our decoder, and then two Kullback-Leibler divergences between the distributions that you see as arguments. A divergence is simply something that is zero if the two distributions that are arguments are identical. The more they diverge, the more it grows in value. So computing the expectation of the left-hand side and right-hand side gives us this famous formula here. Next and last step of the manipulation is to look at these two KL divergences. The one on the right is the difficult one because it contains the correct posterior, the exact posterior of Z, which we don't know. But we know that all the Kullback-Leibler divergences are non-negative, 0 or above. So when we have these, if we want to, we simply ignore, we dismiss altogether the third term. We drop it. In this way, if we drop something that is greater than 0, the right-hand side becomes less than the left-hand side because we drop something, say, positive, technically non-negative. So we're left with this inequality. Now, the quantity they want to maximize to the left-hand side, log P of X, is greater or equal than two terms, the sum of two terms, the expectation of the decoder probability and a divergence, which is a measure of difference between my actual encoder and the prior given to me to learn Z. That prior is analogous to the Dirichlet prior of the LDA, of latent Dirichlet allocation. So it's a learnable prior. Is a learnable prior of Z. The only difference is that it does not depend on the individual document. So it's not P of Z given X, the term that we said is difficult to deal with, and we deliberately removed from the picture, okay? So the quality to the right-hand side is the famous elbow, is the lower bound for the quality to the left, quantity to the left-hand side. The goal is to maximize the sum of those two terms, which is doable, being guaranteed that every time we push that sum up, the log P of X will be at least as high or more, because the quantity to the right is by construction a lower bound, okay? So all the terms to the right-hand side are learnable. The first term is the decoder, P of X given Z. The other term, P of Z given X, is the encoder. And P of Z is this learnable prior that, like in LDA, has to be good for the entire collection of documents or the entire training set. So it is easy to identify its parameters as well, okay? So this is a general variation of autoencoder. The goal is to maximize these quantities. In a way, you could say the first term is the reconstruction error, how well your decoder is able to reconstruct in probabilistic sense your data. And the other term forces the model, which uses individual encoder probabilities for each document, for that to be as close as possible to the prior over the entire collection. It's like a regularization term. First term, if you want, the construction error. Second term, a regularization term. That's another way to look at those two terms. And the derivation is like I presented. You can see the derivation again in every, as I said, handbook is easy, textbook stuff. It's just, I find it the easiest way to introduce it. Other people introduce that manipulation in a different order. For me, that's the easiest way to come up with this formula. That is the training objective of the variational autoencoder. So the very next step, obviously, is how to make use of this in topic modeling. The very first paper I'm aware of that used a variational encoder for topic model is this Meow paper from 2016. The year after, Srivastava and Saran, 2017, published a slightly different model. Meow's model is probably, if you just people, what is a neural topic model, which means a variational autoencoder topic model, they will point you to Meows. Meows is a SageMaker. So if you do a search for neural topic models in SageMaker, you'll come up with the Meows algorithm, which is part of the library. I'm more familiar because of Amit's work with Srivastava and Saturn's model, so I will present that model in the coming slides. Almost equivalent in some sense, very similar. So now the problem is obviously that you haven't seen these, and it takes time to get familiar with the notation. Be sure that you crack the notation's meaning, you understand everything. So don't worry if you don't understand the entire lot. The key information is in this and the next slide. I've created 2 slides where I put all the information that I think is needed. So first of all, the variable Z that we said is using LDA's generative model to represent the topic of a certain word is marginalized. So it doesn't appear, it disappears from the model. That's the reason why I introduced the second version of the generative model, because these models use the second version where Z is not sampled explicitly. All you sample is W, the word itself. Second, the quantity that we put in the formulas Q of theta becomes our only latent variable, the topic proportions of a certain document. Given the document, the bag of word, we call it W. This is a single column, represents the bag of word of that particular document. This is the encoder, and the encoder is taken from a family of distribution, which is called logistic normal. It's a super simple distribution to sample, because all you have to do is first you sample just a Gaussian distribution of k dimensions. And then you take the sample and you pass it through a softmax. After the softmax, the sample is guaranteed to be between 0 and 1. So pretty much you sample the logits from the Gaussian distribution, you put the logit through the softmax, and you get a standard probability value in a probability simplex between 0 and 1 added up to 1. So sampling from a logistic normal distribution is trivial. You first sample a k-dimensional Gaussian, and then you put the sample of the Gaussian through a softmax, and that's the sample of a logistic normal. Now, sampling Gaussians in a variational autoencoder is done with the famous reparametrization trick, which is a big word to simply say that you can obtain samples of an arbitrary Gaussian using samples of a standardized Gaussian of fixed parameter, 0 mean, and identity matrix as a covariance matrix, 0, 1, standardized Gaussian. You can take that fixed Gaussian, use it to generate the samples, and then to make them equivalent to the samples of an arbitrary Gaussian, as you perfectly know, you have to multiply them by the square of the covariance, square root, sorry, of the covariance, and add the mean. So manipulate the samples to make them become equivalent to those of a Gaussian distribution that you want. The mean and the variance that you use to transform the samples are given by neural networks. There are functions which are learned by neural networks of whatever sort. So they're learnable functions that you use to learn this mean. And this is standard variational encoder stuff. So that's how you learn the parameters of that Gaussian. In reality, you don't really learn the parameters. What you learn are the parameters of the neural networks that independently generate the mean and the variance. Inigo, like in that estimator that we discussed some time back. So almost finished. The last simplification that these guys have done to compute the divergence term, the other term, the regularization term, is to use a trick. Instead of computing divergence between 2 logistic normal distributions, assuming that the prior is also logistic normal, they treat them as if they were Gaussian. of same parameters, of same mean and covariance. So they dismissed the softmax. And why? Because the divergence, the Kullback-Leibler divergence to Gaussian distribution has a simple closed form. So the adherence to the prior is computed cheating as if the encoder and prior were both simply Gaussian distributions. Which lead us finally to the objective, which I'm going to present in the next slide, and is the last technical thing I'm going to say today. This is the training objective, sorry, about this model. I'll skip junk a couple of things, maybe if it becomes too much, but this is the training objective of the variational encoder topic models. The first time I saw it, I said, look, gee, I don't understand what it means, and I'm never going to be on top of this, no, so much stuff. In reality, just briefly, this term on top is simply the closed form of the Kullback-Leibler divergence between two Gaussian distributions. The one with parameters index 0, mu 0, sigma 0 is the encoder. The other parameters mu 1, sigma 1 is the prior. Done. The term above is the KL divergence. The term below is the log likelihood of x given z, expected in the sample. There's just one sample per document, typically, no more. And the sample is this epsilon. Epsilon means a sample from a Gaussian distribution of parameters 0, 1. You adjust the covariance first, and then you add the mean. This makes it become equivalent to a sample of a Gaussian distribution of mean mu 0 and covariance sigma 0. After that, because the distribution is logistic normal, and in particular because you need to have a vector of proportion, which is between 0 and 1, you pass it through the softmax. Sigma means the softmax. So sigma of that argument returns a sample of the logistic normal distribution that represents your encoder. Beta, the matrix that has the topic distributions, instead of being kept in the simplex, is kept in the logit scale. So also beta has to be put through a softmax to go back to be a proper probability distribution. You multiply beta times theta. Like we said, you marginalize the topic variables in this way by multiplying the matrix beta for the topic proportions, and you get a single vector of V elements that represents the chosen probability distribution. How well does that match your document? It's the probability of W given this beta mix. But the formula computes it very simply. So fundamentally, that probability is the product, the dot product of the bag of word times the log of theta, or the log of the parameters, log P, let's say. Simply that is the evaluation of the log likelihood of the recorder. Finished. Term on top, prior. Term below, log likelihood. Log likelihood takes following steps, simple steps that are pretty much the steps of every variational encoder. And that's proved to be really good. I mean, the performance of these models, neurotopic models, in all the experiments that we have carried out, unbiasedly, are better than LDA. Better than LDA in a number of ways. So it's a genuinely better model than a standard LDA on all the data sets that we have used ourselves. It's fast to train. Implementations are available publicly. There's no reasons not to use it. Just again, I'm probably going to go a little bit over time, but if you don't mind, I'll say a few more words. The authors, Srivastava and Saran, have actually created two versions of this model. One where they multiply the logits first and the softmax after on the product, and they call it prod LDA. The other one where instead the two single logits are first softmaxed and multiplied after, and they call that NVLDA. Between these two, they have no clear winner. Us, we found prod LDA in general works better than NVLDA, but on par. The original code is all in TensorFlow 1.1, so it's almost unusable these days, but there are PyTorch versions of prod LDA for sure, because we're using it now. So there's public code for both these algorithms. Now, I promise not to talk about research too much. I really just want to give an intuition of what we've been doing with Amit over the last 2 years. We started from these existing variation autoencoder topic models. First, we had to understand them, run them and everything. Then we started to say, how can we improve them? So we started to do a bit of objective engineering. So we started to design alternative training objectives, not really alternative, complementary training objectives, all based on Gumbel softmax, policy gradient theorem, rebar, and similar algorithms. So they're all kind of in the same space of ideas. If you're interested, we can talk about that anytime. This is the classic policy gradient approach. Is an expected risk. The loss L here is the standard loss of a variational encoder. The distribution of the encoder Q multiplies L. Instead of finding the best theta, here we try to find the best expected product, which means a Q encoder distribution, which is able to generate good samples across the entire spectrum of the values of theta. Generating good values of theta means that the expectation will be low, and that's what this objective aims to realize. Various things, we've added baselines, we used rebar, which is an unbiased gradient estimator. We've done a few things. In general, the results have all been quite interesting. As I said, variational encoders are better than LDA, and these results in general have been better than variational encoders. The two typical measures are perplexity and topic coherence, and sometimes you do visualizations like this in topic modeling to show where the topics are in word space, how many counts. So let's skip this because it's too much, just some results. This is some results on a very standard data set, 20 news groups, but also on a much larger one called Amazon Fight Food Reviews, which is almost 500,000 documents, so 500,000 documents. And the models with RB means with our reinforced with baseline variation over the corresponding variational autoencoder model. All of them have either achieved better perplexity, but some have achieved better perplexity and better topic coherence as well. And not just one measure of topic coherence, but two, NPMI and coherence CV. So we've been able to tune them to work to our, of course, there are at least 1 or 2 extra hyperparameters. So not to say that this comes free. There are things to take care of to obtain these results, but the final results were better than the available models. So we come to, I think, the conclusion pretty much. The main messages I wanted to convey were that variational encoded topic models are simple, despite the notational first glance they may look something unapproachable. In reality, the intuition is super simple. They follow straightforwardly the concept of a variational encoder, which in turn is something easy to understand. Use them even easier. They are fast, very quick to train. You can early stop and still get good models. So it's not anything. We found other models in the library of Jensen to be much more computationally heavy in terms of training time. So they're trainable. These variational encoded topic models in all our experiments have proved better than LDA. So the training, fantastic here is that it's all auto-differentiation, is all backpropagation. There is no need to think of an expectation maximization algorithm that first improves this and then improves that. And then it's straightforward backpropagation. Once you write that objective, backpropagation does all the rest. And if you want to play around with the training objective and change the training objective with something else, other objectives, other terms, other regularizers, it's all really very easy to do. And some references after this. That's it.
Cool. Thank you, Massimo.
Likewise, thank you for listening.
It's a good review of the topic. I had a bit.
Never done anything like it before, no? We didn't even mention, I think, topic models in a very formal way at all. But since this has become its own thing for at least a couple of years, I thought it could be good to make it a bit like a shared bit of knowledge across the team.
I have a quick question on the result table. Like, the coherence, if I remember well, was the metric that helped understand, shed a bit of light on how meaningful or how easy to understand are those topics, or is or how the top words, how well related they are to each other, or something like that.
Exactly. So the fundamental assumption in this metric is that there is an assumption that if the model is coherent, so to speak, the words that have the highest probability in each topic, which means if you take the column, for instance, the 10 cells with largest values, have to co-occur frequently in documents. So it's not that the top word appears in one document, in other words, you look at pairwise co-occurrence. So you assume that that pairwise co-occurrence across the, say, 10 top words of a topic should be very frequent if the model is to be regarded as coherent.
Yeah.
Don't know how shareable is this assumption, to be honest. It's just taken for granted because pretty much every topic model uses topic coherence for assessment. The main difference between perplexity and topic coherence, perplexity is very much like the log likelihood. So you need to measure it on an independent test set. Otherwise, you're cheating. You're pretty much measuring the training objective.
Yeah.
But because topic coherence is so different from the training objective, it is legitimate to use it on the training test itself as a measurement of your descriptive capability or explanatory capability over that collection. So you don't need to measure it over the test set. You can report the topic coherence over the training set itself because it's an extrinsic measure that you didn't use for training.
Yep.
That's it. There's at least 4 well-known ways to measure it, and probably more. There are 4 ways in Gensim, for instance. These are 2 of them, but there are more. So the actual definition varies.
Yep. And in terms of like interpretability of the latent variables of the topics, is neural also better, or because when we apply the LDA, often we don't really know sometimes, unless it is a standard data set like news groups where the topics are more like predefined before we know how they are.
Yeah.
We can interpret.
You have a sort of ground truth over the topics, which is not exactly true. But in qualitative terms, all I can say is that my impression, because it really is subjective, highly subjective, what do? You look at the top 10 words of 50 topics or 20 topics, and you compare with the top 10 words of 20 or 50 topics of another model. How do you do that? By eyeball judgment. And topics do not correspond with each other.
Yeah.
And so it's incredibly difficult to say which of either model is better.
Yeah, it's a bit subjective.
It's very subjective, but you can cherry pick some examples like we do with examples in nlP and show that this is a good topic because the top 10 words all talk about coffee and beans and cups and something that appears coherent.
Thank you. Any other question? Anyone?
All right, so we can really call it a day. Thank you very much for coming, especially to you, Junio. It's such an honor to have you in attendance of a humble internal seminar. But I thought that this may be a way to introduce each other. It's great to also maybe now I can recognize you when we walk in the corridors. And if you want to have a cup of coffee or a chat anytime, please just let me know.
Yeah, sure. Thank you.
Thank you for that.
Thanks.
Yeah. All right. So I forgot to stop recording. I'll do it now.